All right, so they've asked us to substitute in for cos squared x. So quickly, using the identity that we know, we can isolate for cos squared x. So we move sine squared x to the other side. Cos 2x now, we just developed this formula, cos squared x minus sine squared x. Now we're just going to substitute in for cos squared x, this 1 minus sine squared x. So cos 2x becomes 1 minus sine squared x minus sine squared x. So you see how this went in for that. Okay? So then we simplify this. It becomes 1 minus 2 sine squared x. And that simplifies to 2 cos squared x minus 1. And that goes again back to this identity. Okay? Any questions with that one?
Can you do that again?
Sure. So we substitute in. Are you good up to here?
Yeah.
Okay, so we have cos, let me see, cos 2x is equal to 1 minus sine squared x minus sine squared x. Okay, everyone's good up till there? So this becomes 1 minus 2 cos squared x and cos minus 1.
Sir.
Hold on. Sine squared x is equal to 1 minus cos squared x. So now we have 1 minus 1 minus 1. So that becomes negative 1, and then we have positive cos squared x and positive cos squared x. So we have 2 cos squared x minus 1.
Why not, instead of just subbing for the sine 2x, why didn't you just solve for, why didn't you just solve for sine 2x and just plug cos 2x in?
Yeah, you could have done it. Yeah, I'm not sure why they went about it that way. It's kind of confusing. They took a lot of early steps and then just skipped everything to go from there to there. Yeah, it was strange. Yeah, there would have been easier substitutions to do than that. I'm not sure why they chose that path. Okay, but does everybody understand this process? So I'm just going to go over it now quickly. So we understand from here up to this point, right? Any questions up till there? Okay, so that's where I took over here. So that's this equation. We all understand this, right? Sine squared x is 1 minus cos squared x. Okay, so I'm just substituting this in now each time. So 1 minus cos squared x goes in for each sine squared x. Okay? And now I'm just gathering like terms. So it's 1 minus 1 is 0. Minus 1 is left. So minus 1 is my constant. And then I have negative 1 times negative cos. So that becomes positive. And this becomes positive. So I have positive 2 cos squared x. Okay? So cos 2x is equal to this. Why might it be important that we have both of these? Anybody tell me what's the point? Why did we develop this one as opposed to using this one? Nobody? It's just to save time. If we're given the cos of the angle, we can solve it just using cos. Okay? Whereas we don't need to have sine. So we just made that substitution so you have two formulas for cos 2x. Okay? Likewise, if we're given just sine x here, we can also solve for cos 2x by solving the equation in terms of sine squared x. Okay, so let's follow along here what they've done. I wonder if it makes a little more sense here. We have sine squared x plus cos squared x. So we isolate for sine squared x, substitute that in to this formula for sine squared x. So there it is. Yeah, this one makes a lot more sense. Okay, it's pretty straightforward. So that gets substituted in for sine squared x. So you end up with cos squared x minus 1 minus cos squared x. Oh no, you don't. You have to substitute back to get this. Okay?
So to get the cos squared x and the second one.
This?
Yeah.
From here. This one?
One up.
This one?
Yeah.
This is from the formula we developed at the beginning of this lesson. Okay?
Oh, and you sub. Oh, okay.
Okay, let's move on. All right, we're almost at the problems here. Repeat part E, but this time eliminate cos theta on the right side to develop the equivalent expression in terms of sine theta. So we did that. So we end up with cos okay. Repeats parts A to C to develop a double angle formula for tan 2 theta. Alright, so here's tan 2x. They even changed the theta to an x in the solution, so they agreed they don't like the theta, it looks like, either. You see that? So in the question it has theta, and then in the solutions they have x. Anyways, okay, so we have tan x plus x. Here's our formula for summation angles from last class. So we have tan x plus x. We substitute directly into that formula. We end up with 2 tan x, 1 minus tan squared x. Alright, so there's our formula for tan 2x. Any questions about that? It was very straightforward. We verify it by using 22.5. We figure out that it's equal to 1. We know tan 45 is 1, so we're good. They verify it again. They actually they get the same answers here. 1 over root 3. They're verifying it for 30 degrees. Okay? The last part, it says make a list of all the double angle formulas you developed. So here they are. We're going to see them again in summary, I'm sure. Sine 2x is equal to 2 sine x cos x. Cos 2x, there's 3 of them, right? We developed 3 of them. One in terms of cos and sine, and then using that trigonometric identity, sine squared x plus cos squared x is equal to 1. We were able to develop in terms of just cos and in terms of just sine. Okay? Finally, tan 2x was the easiest one we just developed right up here. Any questions to double angle formulas? I think it was a lot easier than summation and subtraction formulas. First question, how do we use compound angle formulas to develop double angle formulas? We substituted them, right? Or we used the angle of x and x and substituted. Why were you able to develop 3 different formulas for cos 2x? Because of the trigonometric identity, sine squared x plus cos squared x is equal to 1. Right? Because of that, we can express one in terms of the other. How might you develop formulas for sine x over 2 and cos x over 2? So we could do that just by substituting into the formulas we developed, right? We can recognize that doubling x over 2 gives x. Substitute x for 2x in the left side of the double angle formula for cos, and x over 2 for x on the right side. Simplify. So we know that cos oh, sorry. Right, so we would just substitute this in the formula, x over 2 plus x over 2, and then substitute that in and develop the formula for x over 2. Okay, let's look at the examples. Simplify each of the following expressions and then evaluate. So, quite a lot easier now. This is our double angle formula for sine 2x, right? We know that this is equal to sine 2x, where x is pi over 8. So all we do then is we substitute pi over 8 in for x and solve. Very simple. Next one is tan. The formula is set up perfectly for tan 2x. So we substitute in 30 degrees or pi over 6 for x. So we get tan 2 pi over 6. So we end up with root 3. Any questions about either of these two?
For B, you put in 30. It's just 30 something.
Yeah, pi over 6 is 30. Right? In degrees? Okay. Any questions? So the only tricky part with this is recognizing that this is sine 2x and this is tan 2x, right? That was the only hard part there. So here, if cos x is equal to negative 2 over 3 and x is between 0 and 2 pi, so we're going all 4 quadrants here. If we're looking at 2 pi, determine the value of cos 2x and sine 2x. So we start off with the equation for cos 2x, which is 2 cos squared x minus 1. We use this equation. Why? Because we're given cos x in the question. So we want to express it just in terms of cos. So we can figure out that answer very quickly. Substituting in for cos x, negative 2/3 squaring becomes positive 4 over positive 9. Careful with this negative sign. Make sure you attribute it only to the numerator or only to the denominator. Don't attribute it to both. Actually, it would have been positive in either way, so it wouldn't have mattered, but you should be careful of that anyways. If x is in the second quadrant, so we need to consider now, when we have, when we're given a fraction for the trigonometric ratio, that negative sign can either go with the 2 or it can go with the 3. So there's 2 quadrants we need to consider, right? We need to consider when the numerator is negative 2, or the adjacent side, or we need to consider when the y value is negative. So here's both cases. So if x is in the second quadrant, then cos is equal to negative 2 over 3. Then we can use Pythagorean theorem to solve for the radius. Okay, where this is negative 2 and the radius is 5. Why? Because it's adjacent over the hypotenuse. Okay, that's how we develop and find out that the y value is root 5. Now that y value, as I mentioned, this can either be positive or negative. You get the same values of cos. So we need to consider this quadrant as well. So sine 2x is equal to 2 sine x cos x. We can then substitute in our values for sine and cos and solve for sine 2x. If it's in the third quadrant, the y value, as I mentioned, is negative. So we need to consider sine x is equal to negative y, or root 5, over 3 now. So sine 2x is equal to 2 sine x cos x. So now we substitute in our values, and we get a positive value. Any questions about why this could possibly be 2 answers? And why this is 1? Remember, it goes back to the fact that cos is an even function and sine is an odd function. Okay, so whatever the value of x here, in this case, the cos values will be the same, which is negative 1 over 9. They're both in negative quadrants for cos, left of the y-axis. For sine, however, if they don't tell us what quadrant's in, you have to consider both the second and the third quadrant. Any questions about that? Because this might be the hardest thing we've come across so far in this lesson. This idea. Okay. Moving on. Give tan x is equal to negative 3 over 4. Given. So this is telling us we're in the fourth quadrant, right? Between 270 and 360. Calculate the value of cos 2x. So it tells us we're in the fourth quadrant. So it's really good practice, like we had from 7.1, to really kind of conceptually understand, what this means. We're in the fourth quadrant, and this is tan negative 3 over 4. We have to understand that negative 3 is the opposite side, and 4 is the adjacent side. So when I go to draw it, I know this value here is negative 3, and this value here is 4. Any questions about that and how that was drawn? Okay, because you have to be able to do that. If you can't draw this diagram here, if you don't know how we went from here to here, it's going to be a lot of problems for you in this chapter. Okay, tan is opposite over adjacent. Remember, our angle is here. It tells us it's in the fourth quadrant. If it didn't tell us this, where would the other angle be? Where could it be? There's only one other quadrant it could have been in. Not the first. Yeah, the second. Why? Why the second? I know everyone's thinking, okay, well, it's the related acute angle. It's over here, obviously. But why do we know that from here? Yeah.
Because that's where tan's negative.
Yes, good. Exactly. Okay. Tan's only negative in these two quadrants. Okay. So in this quadrant, the bottom 4 would have been the negative, the adjacent side, and the 3 would have been positive. Here, I know it's down here. Why? Because they tell me right here. That's why. That's the only reason why it's drawn like this. Otherwise, I would have had to draw both angles, just like we did with sine. You guys understand that? I hope so. Okay, so once we have these two sides, it's a right angle, we can solve for the radius, which is 5, just using the Pythagorean theorem. Once we have all three sides of the triangle, we can get any trigonometric ratio we want, and we can solve for cos 2x using the formulas we developed. Okay? Because we have all sides and all ratios, we're going to use the simple cos squared x minus sine squared x. So we substitute in for cos x, which is 4 over 5, adjacent over hypotenuse minus opposite over hypotenuse, both terms squared. We end up with 7 over 25. What would have the answer been in the second quadrant? What would have cos 2 theta been? What would have it been? Yeah, Jungkook? Negative 7 over 25?
Yeah.
Why?
Because it's on the second line.
So you would have had cos. Let's see. Yeah, you're right. So let's see. We would have had here would have been 4.
-4? Negative.
Yeah. So we don't get negative. Why not? Yeah, Nicholas?
They're squared, so
Yeah, because they're squared. Good. Why else? Because cos for the same angle